All right, let's get started. I got a couple homeworks to hand out. Let's see, there and there. There you go. Well, I'm having a hard time getting through all the crowd of people in here today. My goodness. We'll see if a couple people come in late. I'll be humorous with them. Okay, so let's go ahead and sort of get sorted. I mean, everybody's sort of getting back into the swing of things from Thanksgiving break and whatnot. So a couple of things. First off, let's talk about the grade as of now, because we're starting to get near the end. So I want to make sure that everybody is clear on how the grade is computed and what's been done as of now and what's coming. So first off, obviously as of today, the attendance grade is current. Speaking of, I need to pass the sign-in sheet around. So homework 1, 2, 3, 4, 5, and now 6 are graded. And I've got the grades uploaded to Blackboard. Okay, now in terms of homework assignments, how's it going? Hey, my name's Greg Michelson. I teach mechanics in four bodies here at Marshall University. How you doing? Doing good? What's up? It's cold. It's cold. So it was like this? All right, so exams 1 and 2 obviously are graded, and homeworks 1 through 6. So what's left? Homework number 7 is left. That's due on Thursday. We're going to leave room for questions here in a second. Homework number 8 is going to be assigned right after homework number 7. Oh, that's a typo. I have it due Tuesday, November 29th. It's due Thursday, November 29th. That's going to bug me. Yep, that is correct. It is December, I think December 13th. December 13th. Thank you. That's going to bug me as well. Okay. So homework number 7 is due Thursday. I'm going to assign homework number 8 on Thursday. It's due the following Thursday, and then that's it. Okay? So everybody okay clear on homework schedules? Okay? Now, as for the exam is on December 13th. That's Thursday. I have here due 10:15 a.m., but our exam, it's at 8, right? I think it's 8, so I'll check. It's in the syllabus. I checked the exam schedule when I made my syllabus, so it should match. Because I have one exam Monday at 10:15, and then it's Thursday at 8 a.m. That's when our exam is in here, so it's Thursday, December 13th. Okay, so homework 7, homework 8, the exam. Let's talk about this bonus assignment. Okay, so I don't know about other professors, but I take the course evaluations kind of seriously because I like to see the feedback, and I'm always always trying to improve. So I'll give you a story. I told this story yesterday to my structural analysis folks. My first semester here when I taught steel design, I was using these PowerPoint slides that had a dark blue background, and so when you printed them out, on black and white, it was gray. It was a dark, solid gray. And you take a pencil and you write on them, you can't read it because dark gray background with a pencil on it, you can't read it. And so I was looking through my course evals, and like everybody was saying, you got to change the background. Like we can't write on anything. And so the theme that I use now with the green lines and the Marshall logo and whatnot, that's why I use that theme, because if not, I'd have probably been using this blue background this whole time. Okay. The point is, I'm trying to make, I do take this stuff kind of seriously. So here's what I've done. I've taken that course eval and I've combined it with, you all have had engineering classes before, so you know it's usually like the last day of the semester or during the final, you get that little survey where, like for this class, the survey will say on a scale of 1 to 5, how do you feel about torsion? How do you feel about axial loads? How do you feel about Moore circle or whatnot? Well, I said, you know what? Why don't I take that survey and the course eval stuff and let's just do it, make it easier for you all and put it all on Blackboard. So right now on Blackboard, there's a little link for a survey. And all it's asking you are 8 things, or it's asking you, I think it's 8 questions, 8 or 9 questions about outcomes in this class, like how do you feel about stresses and strain, how do you feel about Moore circle, how do you feel about shear and moment diagram, stuff like that. And then there's a link at the end for you to upload an image telling me that you've done your course eval. Let me be absolutely crystal clear. I in no way, shape, or form want to see what you wrote. And you could say I'm the worst professor ever. I just want to see that you did it. Okay? If you do that, I will grant you 10 bonus points on your homework average. So to give you kind of an idea, so you've been doing homeworks, this whole semester, so you know that like homework 1 might be worth 40 points, homework 2 might be worth 30 or whatnot. So let's make up a number. Let's say there's a total of 250 possible homework points. Well, with this assignment, you could earn 260. So like, could you get a homework average over 100? Yes, you could, okay? So all I want to see that you do is that you complete that survey and just do your course eval. I have it set up for anonymous grading, so I don't even know who says what. I just want to see you do it. So, yes. Well, let me ask you this, because what I can't do is, well, 2 things. Number 1, it is set up to not, like you can start it and stop it and start it and stop it to your heart's content, and you can't. I'm glad you said that. What I'm going to do, this is what I'm going to do for everybody in here. I will clear the attempts, and like just everybody's attempts. So sorry if anybody else did it. I don't know. But I'll clear because what I can do is I can clear the attempts for everybody, and I'll set it up for multiple submissions. Because I was going to ask something. Are the course evals open yet? See, I thought that they opened the Monday after Thanksgiving break. They usually do, but I don't know, for some reason they're not. So I'm going to probably, I'll probably close it and then clear all the results and reopen it when I know that the course evals are open. So it might be next week or something. So just do me a favor and remind me if I forget. So sound good? Everybody else okay with that? So homework 7, homework 8, final, and this. And that is mechanics of deformable bodies in a bow. Sound good? Now, topics for today. First off, so I want to open up some room, or if anybody has any questions on homework 7, I'll go ahead and tell you, I can guarantee you there's at least one subject area on homework 7 that you probably had no clue how to address, and that's thin-walled pressure vessels, which is what we're talking about today. I believe that's the last problem on the assignment. When we get through pressure vessels, I think you'll see it's really easy. It's really simple. But other than that, are there any questions on the homework? Is anybody? Yes.
You're supposed to draw it in the orientation, like you just draw like it is, and then you draw
Yes.
some angle, and then you just state whatever that angle is.
That's what. Yeah. So, which is that the first one?
I think it's the
Second one. So yeah, here's your original stress block, and then here's the oriented stress block with a new orientation. I mean, assuming this is right, I don't. Yeah, but yeah, that's what I'm looking for. And then there's one problem where I actually want you to draw a Moore circle. I don't remember which one. That's the second problem? Okay. Yeah, I do. One of the things about Moore circle is that you can apply it without actually drawing it, because you can compute the center of Moore circle easily. You can compute the radius of Moore circle really easily. So if you know the center and the radius, well, tau max is the radius. Sigma 1 and sigma 2 are the center plus and minus the radius. So you don't really need to draw it, but I want you to draw it at least for one problem. You can't get through mechanics of materials without drawing Moore circle at least once. Come on. It's like one of the most fundamental things in the class. It's like calculus and taking a derivative. If you can get through calculus without taking a derivative, let me shake your hand. So, any other questions? Y'all good for Thursday?
the grading synopsis that we have online, is that weighted, percentages added, and everything?
You mean the class average?
Yeah.
Yes. It is weighted. So I'm glad you said that. So let me make sure everybody's clear on the grading. So the attendance is worth 5%. The homeworks are worth 30. Exam 1 and exam 2 are each worth 20%. and then the final is worth 25%. The final just has a little bit more material on it in here. So right now, what Blackboard is doing is it's assuming the final doesn't exist. So it's computing your average based on the attendance, the homework, exam 1 and exam 2. So it's taking like, it's like a weighted average, like 5% times this, 30% times this, 20 this, divided by 5 plus 30 plus 20 plus 20. And so that's how it's computing your average. So dependent on how you do on homework 7 and 8, you can play the at-home game and figure out, well, what do I need to get on the final to get an A or a B or whatnot. By the way, one other thing about grading, I round, okay? So if you have, and there's a reason I'm saying this. So if you have, let's say, an 89.6, I am giving you an A. But Blackboard will say 89.6B. Blackboard does not round, but I do. So if you have an 89.6, Dr. Mike, you said, don't worry, I'm giving you an A, so don't worry about that. But if you have an 89.2, that's an 89. That's a B. So sound good? All right. Any other questions about housekeeping, about homework 7, about anything? All right. Okay. So we only have one more combined loading scenario to discuss, and that's thin-walled pressure vessels. Because they are a special case, if you will, let's just sort of lay it out there. So what I'm talking about when I'm talking about a thin-walled pressure vessel, which let me be frank with you, this is probably, at least on its face, going to be a little bit more of an attractive topic for you mechanical engineers in the room, because, I mean, we're talking about storage of, fluids, gases, what have you, at either high temperatures or high pressures, so that's like a mechanical engineering aspect if I've ever heard one. There are actual applications of thin-walled pressure vessels in civil engineering as well. For those of you who choose to take reinforced concrete design, when we look at spirally reinforced circular columns, we size and detail the spiral reinforcement, assuming it's a thin-walled pressure vessel containing the column. You've got this compressive load on a column. The internal column wants to crack and burst, and then the spiral reinforcement is keeping it contained. So it's kind of the same thing. Now, a couple things about this derivation and how we go about it, because, again, you're going to see these formulas, and they're really simple. This is really straightforward. What we're talking about in this derivation is we're talking about a vessel. We assume it's cylindrical in nature, so it's a long, circular tube, and it's subjected to some sort of uniform internal pressure on its inner surface. Now, one of the things that we're doing in our analysis is we are assuming that the walls of this cylinder are essentially thin. Okay, and what I mean by that is that you're really not getting a variation in response from this side of the surface to this side of the surface. In other words, we're basically assuming that the stresses and strains are uniform along the wall of the cylinder. Okay, there is another more complex theory that you like. For those of you in mechanical, you might actually talk about thick-walled cylinders in maybe like a mechanical design class or a machine element design class or something like that. That's very possible. And that's when you take into account that the strain varies along the thickness of the wall. For you mechanical engineers, this is kind of random, but this is a really cool application of thick-walled cylinder theory. In any of your mechanical engineering classes, have you ever heard the term auto-frettage? That term ever popped up? Okay, so when you're designing a gun, okay, you've got the gun barrel, okay? Well, I mean, what's going on with a gun barrel? You shoot a gun, and you've got this bullet or projectile going through the gun barrel at a very high temperature and velocity, okay? And that subjects the inside of the gun barrel to a very significant internal pressure, okay? If you were to fabricate a gun barrel and not take into account the concept of auto-frettage, you'd fire that gun maybe once or twice, and then that gun would be trash, okay? What you end up doing when you design a gun barrel or any type of thick-walled cylinder that's going to be subjected to very high temperatures and pressures is you actually start off, you fabricate the cylinder, and you start off by actually subjecting it to a very, very large internal pressure before you use it. And the reason why is because you actually force the inside of that cylinder to yield. Okay? The idea is if you have a stress strain curve, right? So let's say here's your material, right? Let's say here's your material. Let's say it goes like that. If you don't force internal yielding before you use it, it can only see a stress of about this high before it starts experiencing plastic deformation. But if you actually yield the inside of it and force inelastic behavior, you can strain harden the inside of the cylinder and it can experience larger stresses. So you actually fail the cylinder so that you can use it repetitively. So random tidbit, random factoid, but that's all I got. I just think that's kind of cool. It's called autofrettage, if you ever hear about it. So Google it, Wikipedia it. It's cool stuff. Okay, so what we're doing in this derivation is I'm ultimately trying to determine the stresses on a thin-walled pressure vessel that's subjected to internal pressure. Now, this is pretty simple to understand conceptually if you think about it. You got a balloon, right? Take the balloon. Balloon expands. What type of stress is the balloon experiencing? Think about it. I mean, let me ask it simply. Is it experiencing tension or compression? Take the balloon. What happens to the balloon? The fabric of the balloon is being stretched, right? That's the same thing here. You have a pressure vessel subjected to an internal pressure. The pressure vessel is wanting to expand, but it's not. It's containing that pressure. So it's going to experience some tension. If you look at a stress block in a pressure vessel, like, you know, here's your stress block, what you end up seeing is here's a sigma 1 and here's a sigma 2. You end up seeing a stress block that experiences nothing but tension. So your principal stresses are really easy to determine. Once you get sigma 1 and sigma 2, you can determine tau max pretty easily. So that's really sort of the long and short of what we're doing, is we're trying to determine sigma 1 and sigma 2. Okay, so I have here a section of a cylinder, right? And I'm taking out my samurai sword or lightsaber if I'm a sci-fi fan, and I've cut some sections. Now, what I'm doing is I'm looking at a section of this tube, but not only am I looking at a section of this tube, but I've cut it in half. Okay, so I'm only looking at one half of the pressure vessel. Now, if I look towards the pressure vessel, I propose that that pressure vessel is generating some amount of tensile stress, some sigma 1. Okay, some sigma 1, and that I'm trying to determine. I want to know what the tensile stress inside that pressure vessel is. Now, that tensile stress has to counteract the pressure inside the pressure vessel. Well, what's the force generated by that pressure? Well, I propose that that pressure times that area is the amount of force that that pressure vessel has to withstand. Okay? Now, in terms of some nomenclature, I've got P for the applied internal pressure, I've got R for the radius, T for the thickness, and B for the width of our section cut. But let's explore this a little bit, okay? Because those of you who've had like a fluids class, yes? The internal pressure inside the section. Now, for those of you who've had a course in fluid mechanics, or if you've talked about pressure a little bit in any of your other classes, you might be a little confused right now, because if you have, let's say, go back to the balloon analogy. If I blow a balloon, the pressure doesn't just act one way. It acts every way, you know. You put you have a pressure vessel or balloon or anything, and you have some internal pressure inside that structure. The pressure is going to act perpendicularly everywhere, because it's going to try and force the whole thing apart. Okay. Well, what I've done in this particular section cut, because I'm trying to determine the amount of stress this way, is I'm cutting a section and I'm only looking to the right. It doesn't matter, I could look to the right or to the left, it doesn't really matter. But the reason why I'm only considering pressure that's acting to the right is because if you look at this section, you know, cut a section, look to the right, everything that's going up is canceled out by everything that's going down. You know, think I've got some amount of pressure going up, I've got some amount of pressure going down, all that gets canceled out. The only thing that doesn't get canceled out in this equilibrium scenario is pressure going to the right. Well, where does that go? Well, it's resisted by some stress inside the pressure vessel acting to the left. So that's why when I cut a section, all I have to consider is pressure acting toward the right, because that pressure acting towards the right is counteracted by the cylinder generating stresses to the left. Everything going up and down is canceled out internally. Does that make sense? From an equilibrium standpoint. It'd be like this. If I have, let's say I'm not going to I'll use my coffee, but I'm not going to actually press on it. But if I had 20 pounds going up and I had 20 pounds going down, well, that's it. There's nothing left to figure out from a static standpoint. That's it. It's 20 pounds. Go home and have a cookie. But with this, because you have stresses going in all sorts of different directions, what we can do is we can say everything going up is canceled by everything going down, but that doesn't address things going to the left or right. Sound good? Okay. Now, here's our section. So how do we determine the pressure and the area and the force? Well, what is this area, right? Well, this area is the width times the height. The height is 2 times the radius. So this area times the internal pressure, that's the force, right? Force equals pressure times area. Sound good? So take that force and divide it by the area of the cylinder. Now, what's the area of the cylinder? Well, the area of the cylinder is the area of this little, I guess we'll call it a metal strip, this little metal strip here and this metal strip there. What's the area of that metal strip? Well, down here it's B times the thickness. Here it's B times the thickness, so it's 2 times B times the thickness. Take force divided by area, there's your stress. That's simple. So, I propose that one of our principal stresses is PR over T. The pressure times the radius of the cylinder divided by the thickness. That's simple. I told you, this is really easy. This is a really easy formulation. Okay? Now that is stress this way. So let's say here's my pressure vessel. That's stress this way. Like we sometimes call it like hoop stress. That's stress along the circular direction of the cylinder. But what about this way? There's also stress acting this way. I mean, think about it like this. If I'm subjecting this cylinder to internal pressure, I propose one of two things is going to happen. Not only is it going to want to get wider, it's going to go like that, it's also going to want to get longer, right? Imagine the clown with the balloon going like this, it wants to get longer. Well, same thing here, okay? So I can use a very, very similar derivation to determine the internal pressure or the internal stress generated along the wall, okay? So what do I got going on here? Well, what's the pressure? Well, the pressure generated by the gas or the fluid or whatever's inside the cylinder is P times pi r squared, because that's the area of this face. What's the area of the cylinder? Well, the area of the cylinder, the area of this little metal ring, is the thickness times however long that is. And however long that is the circumference, right? So 2 pi r times that thickness, that's the area of the cylinder. So I got a pressure, I got a force, I got an area of the cylinder, divide, and there you go. And not only does the formula come out really easily, there's a really easy comparison you can make to your first stress. So I propose that, for instance, if you generate, let's say, 40 KSI of stress this way, you're only going to generate 20 KSI of stress this way. Pretty simple. I'm telling you. That's it. I wish I could, complicate it. I really do. It makes, problems a little boring, but that's like it. Any questions? Okay, let's look at an example. Okay? What? Yeah, let me say that. Our derivation is assuming that the end of the cylinders are flat and it's a cylindrical cross-section or a cylindrical shape. There are derivations, and you can look it up. It's not like it's that difficult to find. But there are derivations for if you have spherical ends or if you have conical ends or stuff like that. Have you ever heard of if you've worked in the field, have you ever heard of a Rourke's stress guide? Have you ever heard of that? A Rourke's stress guide is go to any mechanical engineer who's been practicing for 10, 15 years, or even a structural engineer who's been practicing that long, and look at their bookshelf. And more often than not, you can find a Rourke's stress guide. And basically what a Rourke's stress guide is it's a book about yay thick. And it's got all these different stress formulas for really, really unique scenarios. Like what's the stress on an angle bracket with a hole in it? Or what's the stress on a cylinder with a convex end or something weird like that. And there's oodles and oodles of tables for stuff like this. Like what we're doing is fundamental stress analysis, but if you ever have anything with a really, really weird geometry, I would suggest one of two things. A, if it's something somewhat standard, you may be able to find it in something like a Rourke stress guide. Or B, if it's that funky, break out the finite element analysis. Break out, ANSYS or NX or whatever whatever software package you want to use and determine it accordingly. So does that kind of answer your question? So short answer is yes, there are derivations for other geometries, and I'm not really worried about that in here. As long as you understand the general concepts, I'm good. So, sound good? All right, any other questions? All right, so I have a pipe carrying steam at 500 psi, so that's the internal pressure. I have a pipe that has an outside diameter of 16 inches and a wall thickness of 3/8 of an inch. I want to determine the principal stresses and the maximum shear stress. Also determine the orientation for maximum shear stress, okay? And a hint on that is to use more circle, but I think you'll see where we're going at with that. Sound good? Okay. So right off the bat, let's let me lay out a couple things. So excuse me. Okay. So we have an outer diameter of let's see, 16 inches, and we have a thickness of 3/8 of an inch. So right off the bat, how do we determine an inner diameter? Anybody remember? Take the outer diameter and do what to it? Minus 2t. There we go. Okay, and that comes out to be what? 15 1/4. So the reason why we need that is because we define the radius as that inner diameter over 2. So that is 7.625. Okay. All right. Also, we have our internal pressure of 500 psi. So if you have that, you can determine your sigma 1 and your sigma 2 very, very easily. Okay? So sigma 1 is PR over T. So that is 500 psi. R is 7.625 inches. And then T is 3/8 of an inch. What does that come out to be? There we go. What are the units? It's a stress, so it's PSI. Keep it simple. Look at the, you have a PSI, right? Multiplied by inches over inches. The inches cancel, so it's just PSI. Now, I'm lazy, so you could say that sigma 2 is PR over 2T, but I'm lazy. That's just sigma 1 over 2. So 10,166.67 PSI over 2. Say it again. Sound good? So here's what I propose. For this pressure vessel, we have a stress state where we have a positive 10,166.67 psi for sigma x. We have sigma y, which is 5,083.33 psi. And we have a tau xy, which is 0. Because again, it's a pressure vessel, right? It's like the balloon blowing it up. We're stretching on it, but why am I saying tau xy is 0? I mean, think about it. When you blow up a balloon, is it doing that? No, it's just, whoosh, you know, it's just experiencing normal stress. So from these, what can we compute? Well, what is sigma average? How do we do that? Remember that? Here we go. All right. And what does that come out to be? So just that plus that divided by 2. Yes? The tau xy, the shear stress. $76.25. Do I have a second on that? PSI. All right. What about the radius of Moore's circle? Because remember, that's the center of Moore's circle. We need the radius. Remember how to do that? Move that down a bit. There we go. And so what does that come out to be? Excuse me. They got an answer for me?
2541.67.
Second on that? All right. So from these, we can determine a few things. We can determine sigma 1 and sigma 2. Some of you might have a little bit of a confused look on your face, and that's a good thing. And you'll see why. So what is sigma average plus R and sigma average minus R? What's the first one? What about the next one? There you go. In other words, our derivation, and I sort of wanted to wait until you saw it, but when we derive these right here, these are principal stresses. And I'm going to put a caveat on that, and I'll put if no other stresses do all caps consistently are present. So what I'm getting at is if you were, for instance, let's say you had a cylinder and you were bending it or something, or twisting it or yanking on it or something, then those might not be principal stresses. But if all you have is a pressure vessel with those internal stresses, not only are your stresses easy to compute, but they are principal stresses already. So that's pretty nifty. Now, why did we go through all this crap? Because there is one thing we don't have, and that's tau max. What is our maximum shear stress? No. On a given orientation, what from Moore's circle, what's our maximum shear stress? It's the radius. So at a given orientation, we might find a higher shear stress. And depending upon the material that you're using for your pressure vessel, you might have a material that has a really good capacity when subjected to normal stress, but it might have a really weak capacity when subjected to shear stress. So your shear stress might govern your design, just depends on what material you're using. So I'd say if it's like steel, probably not, but who knows. Now, the only other thing left to determine on this problem is your principal orientation. Now, does anybody remember that formula? Well, you've got your notes. There you go. Now, without doing any math, tell me what that comes out to be. Well, you have to do a little bit of math. You can probably do it in your head. What is tau xy? So what's the inverse tangent of 0? 0. Boom. Again, when you have a pressure vessel, go back to the balloon scenario. When you blow up a balloon, is it doing that? Is it like shearing? It's not. Anytime you have a pressure vessel, if all there is pressure, you're going to have a sigma x and a sigma y, but no 0. No. I'm saying what if you took the cylinder and twisted it, or what if you took the cylinder and sheared it? Then you'd have a shear stress. So, which is possible. I mean, you could take. I mean, imagine you've got the clown blowing up the long balloon. Then you take that balloon and you twist it. Now that balloon is subjected to shear stress. Any other questions?
So, I guess if it's a cylinder, does it really matter if the angle is different?
What?
Like if it's a cylinder, at principal angle, it doesn't matter what it is, right?
It only matters if you're. It only matters if you're using a material that has a particularly weak capacity in shear. It's possible. Look, you look up you have a material. Let's say you're using some grade of aluminum, and that might have an allowable normal stress and an allowable shear stress. So, depending upon what those values are, these may be fine, these aren't. That's what I'm saying. It just depends on the material you're using. Did I convince you? I feel like I didn't.
Well, I'm talking about the angle, not necessarily the PSI, like that principal angle of orientation.
it would only, all right, how about this? The best way of answering that is this. If you had other stresses, then you would need to determine that angle. I'm saying if all you have is internal pressure, then the answer to your question is mostly correct, yes. But if you have a shearing or a torsion or a bending or something, then that angle isn't going to be zero because you're going to, looking at here, you're going to have these values aren't necessarily going to be these, and then you might have a shear stress. Sound good? All right. Since we got time, I'm going to use that time. But we're going to talk a little bit about our last topic. And here's why we're going to talk a little bit about this last topic. I'll make you a deal. If we can get through buckling today and Thursday, we'll cancel class on Tuesday. Are you sure? I'm sensing some doubt. Let's talk about buckling. Buckling is our last topic in the class. So first off, that's homework 7. From here on out, this is homework 8. Okay, and this is your final homework assignment. This will be on the exam, and this is probably it's our last topic in the class, and it's the topic that's kind of unique because it flies a little bit in the face of all of the math that we have generated up until this point, but it doesn't change the fact that it actually happens, okay? So what's the deal with buckling, okay? First off, I think the concept of buckling is one that's pretty easy to understand physically, okay? Imagine if I had a yardstick in my hand. I can take that yardstick and I can yank on it all day long, and I'm probably not strong enough to rip it apart. But imagine if I take that yardstick and I press on it. A few pounds, boo, it bows, right? That is because of the very nature of the way stresses behave in tension versus compression, when you have a member that is subjected to compression, and particularly a member that is slender, okay? And this word slender, we're going to have an actual real definition for what slenderness is here in a little bit. But when you have a member that is fairly slender and it is subjected to compression, what ends up happening is you generate a geometric instability in the structure, and it begins to suddenly and drastically deflect. So you have the yardstick, you start pressing, and boom, it bows, okay? That sudden geometrical instability has a name, and we call that buckling, okay? And so buckling is a very unique science, is a very unique aspect of mechanics of materials, but it's very important, okay? Let's take wood. If you look at wood from a material perspective, like take slenderness out of the equation, wood is about as strong in compression as it is in tension. It's not like wood suddenly changes its properties. And the same thing would be true. We could make a yardstick out of aluminum or steel, or it wouldn't really matter. We can pick just about any material where the material behavior doesn't really change if it's compression versus tension. But take that material and construct a very slender element and put it in tension versus put it in compression, and it will behave wildly differently. If you take a common yardstick, it can carry about 500 pounds in tension. But in compression, only about 6, and it's gone. That is a big deal, okay? That is a very big deal. And just about whether you're a civil engineer or mechanical engineer, remember how I said that civil engineers and mechanical engineers, just about everything they design have something in it that's being bent? Well, at the same token, just about anything that you design has something that's being compressed, okay? So if you're a mechanical engineer, just look at a car, how many different things are being pressed on. If you're a civil engineer, you got beams and you got columns, okay? For you civil engineers that are taking steel design with me next semester, the concept of slenderness is something that we're going to spend a long time on in steel, because how you handle slenderness in different directions is you got to, hike up your pants and know what you're doing. Okay, now stability-related failures is, they can happen for a number of things. For instance, thin-walled cylinders subjected to external pressure. What if you have a thin-walled cylinder that's subjected to pressure externally? How many of you have crushed a Coke can? That's what we're talking about. What about compression flanges in beams? What if you're talking about a beam that's being bent? Anytime that you have a beam, some of it's experiencing compression and some of it's experiencing tension. So maybe the beam will want to buckle. This is just a few, but I mean, there's oodles and oodles of different ways that an element can buckle. And sometimes if you're doing just like an elastic stress analysis, like how many of you mechanicals did stress analysis with NX? Did you all do that? Like you built a part and then ran the stresses? Well, you run a stress analysis, or for you civil engineers, if you run a RISA analysis, all it's doing is just giving you just like here's the compression in this truss member and all this, but it doesn't answer whether or not that member is going to buckle. So the stress analysis that we've answered or that we've done up until this point will give you stresses, but it doesn't consider the concept of buckling. Considering buckling, you can have a much worse scenario. The stresses can be a lot worse. Now, in order to derive how we address buckling, let's consider the following column. So it's simply supported. So I'm saying I've got like like a hinge here and like a roller here. I'm tilting it up, but basically I've just got like a beam that I'm pressing on. Okay. So I have some compressive load on it, and I want to determine what load will cause it to buckle. Okay. Well, I propose that when it buckles, it's going to look something about like that, right? That's what it's going to look like. Well, it's, first off, it's going to bow out. Second, if I've got P going down, I got P going up. So that's really the only difference here. What I'm going to do is I'm going to break out my samurai sword or lightsaber. I'm going to cut a section at some distance X. I'm going to say, well, what I got going on in this section? Well, if I look down, if I've got P going up, I got to have P going down. So right off the bat. And then what about my moment? Well, this is basically like a beam. There's going to be some internal moment inside the column. So how do I determine that moment? Well, if I sum moments at the cut, what do I have? I have some internal moment going this way. Don't have to consider that, but I've got P times Y. Y being however far the column is bowed out, right? So this moment has to equal minus P times Y. Sound good? Now, that Y is not just some innocuous term. That Y is deflection. Remember this? The second derivative of deflection is m over EI, or Y double prime is m over EI. Y'all remember that? That's something we should be, I just gave you homework back on that. So if we have our expression m is minus P times Y, that's what I got from the previous slide, and I know that Y double prime is m over EI, I can substitute and I can get this. All right? Rearrange it a bit. So put everything all onto one side, and then to make the math simpler, what I'm going to do is I'm going to call this term alpha squared. You're going to see why here in a second. Take this term, call it alpha squared, and I get this. Okay? That is a second order differential equation. So now we have to solve a differential equation. So I'm going to use the most popular method that college students utilize to solve differential equations. Acting like I don't know things. I know things. We don't do this, Dr. Mike. We don't know what you're talking about. So Y double prime plus alpha squared, and there it is. Okay? I'm joking. I'll show you, the real way that you would do this. But I have a second order differential equation. The reason why I called that term alpha squared is because this differential equation, Y double prime plus A squared times Y, is a very common differential equation. It's like one of the most common differential equations that you learn to solve when you take Math 335. The solution to that equation is, an arbitrary constant times the cosine and an arbitrary constant times the sine. See, the reason that you call this term alpha squared is because your solution has C1 times the cosine of alpha, C2 times the sine of alpha. Sound good? Now, that's I know that Wolfram alpha is a very common, tool. If you take Math 335, you will learn, the method of characteristic equations. You take your second derivative and call that an r squared. Your first derivative will become r. Your would become a constant. So you take this differential equation and you turn it into a linear equation. You solve for r, and you get r is plus or minus, what, alpha I, right? Because that's imaginary. And anytime you have imaginary roots, your solution will be y equals c1 times the cosine of whatever this constant is times x plus y, or plus c2 times the sine of alpha x. Now, if you haven't had differential equations, one thing to keep in mind, why do I have two constants? Like, why do I have two terms? Because I have two answers here. There's a plus alpha I, there's a minus alpha I. So when you have two solutions, two arbitrary constants that you got to solve for. So you'll learn this in Math 335 if you haven't had it already. But, okay. All right. Oop, I need to erase this. Okay. So when you solve your differential equation, you're going to get the following solution. You have C1 times the cosine of alpha x and C2 times the sine of alpha x. Remember, alpha is the square root of P over EI, and just keep that in mind. Okay. Now, when you have unknown constants, you have to solve for those constants utilizing boundary conditions. That should be familiar because we did that for beam deflections, right? Remember, when you have a beam deflection, you get two constants. How do you solve for them? Well, if it's simply supported, you know that the deflection over here is 0 and the deflection over here is 0, right? Well, it's no different. We're going to do the exact same thing. So, since this is a simply supported column, I propose that the deflection at x equals 0 is 0, and the deflection at x equals L is 0. So let's take these one at a time. Let's take the first one. If I take the first one, utilizing the first boundary condition, so plug in 0, C1 times the cosine of 0, C2 times the sine of 0. What's the sine of 0? That's 0. What's the cosine of 0? That's 1, right? So I propose that first constant is 0, and that simplifies my equation a little bit, right? Now, what happens here is if I plug in x equals L, I get this. That's not what I really wanted. I wanted a nice, pretty little answer. Like, here's C1 equals 0. I didn't get C2 equals something. I got this. What the hell do I do with this? Well, we got to put our thinking caps on. We got to think about this a little bit. We have C2 times the sine of alpha L equals 0. Ignore all the mechanics and the buckling and whatnot. Let's just use some common sense. Okay? How can this equation be 0? Like, I'll give you for instance. Could this equation be 0 if L was 0? Like, what if L was 0? Would that be true? Now, what's the problem with that? Physically. Like, what if L equals 0? What does that mean? The column doesn't have a length. So that doesn't make any sense, right? Could alpha be 0? Right? Alpha could be 0, but what's the problem with that? What is alpha? Remember, it's the square root of P over EI. If alpha equals 0, what that basically means is we don't have any load on the column. So it can't be that because that means we have a column of no length. It can't be this because we don't have a column of any load on it. What about C2? Could C2 be 0? Yeah, but what's that mean for our answer? That's 0, we don't have any deflection. And I know that that doesn't happen because if I take a yardstick and I press on it, it bows, right? So what's the only other option? This can't be 0. This can't be 0. This can't be 0. But what about that? What about the whole sine function? If the sine function is 0, that equation would be true, right? Think about that for a little bit. All right? What we're talking about here is what's called trivial solutions, okay? You can't have an L equals 0 solution because that indicates the column has no length. You can't have an alpha equals 0 because that indicates the column has no load. But this sine function, maybe not so trivial. What does the sine function look like if I plot out the sine function? Doesn't it look something about like that? The sine function doesn't equal 0 everywhere, right? It only equals 0 at integer multiples of pi, right? It equals 0 at pi, at 2 pi, at 3 pi, at 4 pi, you know, so on and so forth, right? Excuse me. So I propose that the only non-trivial solution to this equation is when this term alpha L is n pi, n being an integer. So pi, 2 pi, 3 pi, 4 pi, what have you, right? So the only way that this equation makes any sense physically is if alpha equals n pi over L, where n is an integer, okay? Well, alpha squared is p over EI, so this term's got to be p over EI. Plug and chug. What am I solving for? I'm solving for p. Why am I solving for p? That's what I'm after. How much load causes it to buckle, right? That's what I'm after. I want to know what p is. And so I solve for p, and I get this. Well, what is that a function of? It's a function of pi, well, pi is easy to calculate, e, I, L squared, and then n being some random integer. What do I do with that? Well, let's just look at this. N is an integer, okay? So I propose I get a different buckling load for each value of n, okay? However, we're going to find that only one of them really matters, okay? But just so everybody's clear, we now have an expression for what does the deflected shape of the structure look like and what's the critical buckling load, okay? So it's pretty easy. Now, if I plug in an n value, let's say, of 1, I'm going to get a buckling load. If I get a value of n equals 2, I'm going to get another buckling load. N equals 3, so on and so forth. So here's what that looks like. If I plug in n equals 1, because it's n squared, I get pi squared EI over L squared. If I plug in n equals 2, I get another one, n equals 3, so on and so forth. Okay? Now, let's just keep this simple. All right? I got the yardstick in my hand. I'm pressing on it. What does it look like when it buckles? Does it look like this? What does it look like? This one, right? Look at the loads. In order to generate this mode of buckling, I got to have a load that looks something like this. In order to generate this mode of buckling, I got to have a load that looks something like this. Think. This is 4 times that much load, right? I'm pressing on the yardstick. As I'm pressing on the yardstick, I'm going to hit that before I hit that. So what's the only buckling load that matters? That one. That is the only one that matters. So I propose to you that the critical buckling load for a pin-pin column is this. Pi squared EI over L squared. That's an important parameter. That's one to star in your notes. I'm going to modify it a little here in a little bit, but you'll see why. Okay. Sound good? Now, that is a critical buckling load. This is mechanics of materials. I would like to determine a critical buckling stress. Okay? Now, critical buckling stress, if I'm taking this column and I'm pushing on it, I propose that that critical buckling stress is P over A, right? P over A. So take this and divide it by the area. When I divide it by the area, I can pull out that term in parentheses, okay? That term in parentheses is a section property, right? Let's go back to our discussion of section properties. Remember we had areas and J values and section moduli and moments of inertia, and they were all functions of what the shape looked like, right? All functions of what the shape looked like. Well, this I over A, it is also another section property. We have a special name for it. We call that name the radius of gyration. Specifically, it's the square root of I over A. Remember this? Remember I told you that there's one value in this table I'm going to explain later, and it's that one? Boom. I explained it. In order to compute a radius of gyration, so like let's take this 12.9 right here. This 12.9. 12.9 is computed by taking the square root of 10,300 divided by 62.2. the I over the area. Check it if you don't believe me. I mean, I promise you that that is the radius of gyration. Promise. And so just like with bending, there is a strong axis and there is a weak axis. Okay? Now here's where your conceptual understanding needs to be kind of important. Let's go back to the yardstick. The yardstick, is it going to buckle about its weak axis or its strong axis? Like which way is it going to bend when it bends? The easy way or the hard way? The easy way, right? So when in doubt, usually when you're computing buckling loads, you don't use these properties. You use those, the weak axis. Think, the yardstick isn't going to buckle about that rigid, stiff axis, right? If you compute a buckling load using these properties, it will come out much higher than the buckling load computed from these properties. And that's a big deal if you're a designer because you might be over-predicting what it can really carry. Okay? So when in doubt, always go with the weak axis. Sound good? Yes. It's the square, no, we're defining a new section property as a result. Okay? There's a reason why we define it in this term, and it's going to become very clear here in a second. All right? If you rewrite this equation, this I over A is R squared. So you have R squared over L squared. You can rewrite this like this. This term L over R, first off, L over R is unitless. Because the member length will be like, so many feet. The radius of gyration will be so many inches. So you can do a unit conversion to get that to a unitless quantity. It is a very explicit parameter in buckling. And it's the slenderness. So it's our mathematical way of defining how slender a member is. For instance, if you compute L over R for a drinking straw and compare that to L over R, let's say, for a can of Campbell's tomato soup, okay? You're going to find that the L over R for the drinking straw is much higher than the L over R for the can of tomato soup because the can of tomato soup is a much more compact shape than a drinking straw, okay? And the way that we express that is through a unitless quantity called slenderness, okay? The more slender a section is, the more susceptible it is to buckling. What? That's a great question. That's a great question. So slenderness is just, hold on, let me be clear of something, okay? So slenderness is just a general measurement of the shape, okay? But what you're bringing up is actually a very interesting point, okay? Because you're talking about the thickness of the wall. In other words, if you had a Coke can versus a Coke can where the walls are this thick, it'd be a whole lot more difficult to buckle. And you're exactly right. If you choose to take steel design, because you're civil, right? I don't know about how you mechanicals handle this, if you handle it in one class versus another, but I know in steel design we talk about this very explicitly. There is a difference between what's called global buckling and what's called local buckling, okay? So let's take like a column that's an I shape, okay? Global buckling is the whole column wanting to curve out. You press it and the whole thing wants to curve. Local buckling is, instead of the whole thing wanting to curve, maybe one of those flanges crinkle before the whole thing does. Or maybe one of the web, maybe the web crinkles before the whole thing does. That's local buckling. In other words, the analogy for the Coke can is instead of the whole Coke can curving, maybe just the walls crinkle, okay? That is the difference between global buckling and local buckling. In civil engineering applications, specifically when we're looking at like I-shapes subjected to compression or whatnot, there's a very methodical process on how to determine whether or not global buckling is going to occur before local buckling or vice versa. For you mechanicals, if you're not dealing with a rote plug and chug scenario, it was probably going to be a scenario where you got to break out the software and do the analysis. So, and usually the way that those software packages work is you'll build a big model of your engine or your bracket or whatever it is that you're designing, and you run what's called an eigenvalue analysis. And the eigenvalue analysis, whichever is the lowest eigenvalue, that's the buckling mode that you need to consider. So I know I'm going off on a tangent here, but tangent, sines, cosines, and tangents. Oh my. Walking right into it. All right, any other questions so far? Okay, here's what I'm going to do. I am going to stop for today, and here's why, okay? Right now, are you all okay with this equation? Okay, Thursday, I'm going to introduce this equation. What's the difference? There's a constant. There's a value k. Okay? K is what's called an effective length factor. Okay? The reason for k is because that entire derivation that we just did, we assumed a simply supported column. Well, what if it's not simply supported? What if it's like a light pole in the ground where it's fixed on one end and it's free up top? How does this equation change? I'm going to hold off because I don't want to information overload you, and we have plenty of time to complete not only these series of notes, but we have 2 examples at the end, and we can handle that pretty easily in class Thursday. I'm going to stop for today, okay? So just so you are aware, I think we're planning on canceling class on Tuesday, because if we finish buckling Thursday, that's the class. We're done. So my plan, we lecture Thursday. I give you your homework on Thursday. We cancel class on Tuesday. The following Thursday, we have our exam review and you turn in your homework, which means if I cancel class on Tuesday, we will not have a collected time together where you can ask questions about your homework. The only thing at that point is if we're still canceling class, just email me. Sound good? Then our last lecture is Thursday. The next Thursday, but that's going to be exam review. So, sound good? That's all I got. Text your friends. What's going on now? Hold on one second.